So with that, Professor Kalinin, it's you.
Fantastic. Thank you for introduction, Jay. And I think that the future hasn't started yet, but we definitely are in the moment when this inflection point is visible. And kind of how can we start into that? I mean, we all know that the world is really a materials opportunity. So ultimately, everything that we make is based on the materials. So all the real value in the world starts with someone making a material and making something out of this material and then integrating those some things. And in the end, we have things like internet, satellite communications, quantum computing, and so on and so forth. So practically, however, for materials, we can distinguish several tasks, right? So we need to improve materials that are already out there. For if we make the grid wires just 30% more conductive, that's a huge saving and minimization of fire damage and so on. So if we make structural materials 50% more stable, you can imagine how much it will affect transportation, construction, and so on and so forth. We want to discover materials. So room temperature superconductivity is, of course, one of the holy grails. And that's why there is so many strange stories about it going on. Obviously, superconductivity at room temperature is not enough. We also want to have a sufficiently high current densities, but we know what we need. High mechanical stress materials. So many of you have read sci-fi books about the space elevators. So in order to build a space elevator, essentially we need materials with much higher mechanical stress tolerance that we have now. Engineering, so quantum computing, single atom catalysts, biomolecules, all of this about making materials and molecules. And as material scientist, I obviously include chemistry as the part of materials as well. So the problem is that if we want to make materials, functionality is only half of the story. We also need manufacturability and we need cost. So it's important to say that material science, of course, cannot change overnight, right? It's filled with the huge inertia. But what's happening now, and now being maybe plus minus kind of 3 years, is coming very close to the overnight. So the previous time when the scientific world changed that much was in the early 90s, when the personal computers were introduced. But the introduction of the personal computers was a slow process. So buying a PC at that time was not a trivial thing. So now we are not limited by hardware. We're limited by how fast we personally can learn to do things because the software is already out there. However, the important thing is that just staying in the realm of theory and machine learning can only get you so far. So quoting the Oppenheimer from the eponymous movie, at some point you actually need to get in the lab and get stuff done. So just predicting is great, but things needs to be made. And then the question becomes, how can we bring the machine learning to the real world and produce the real world value? So let's look a little bit at the history. So the big inflection point in the machine learning and materials was about 20 years ago when the Gersitter paper came out in 2006. And it's interesting that in the 2006 also AWS appeared. So what it means is that, first of all the theorists realized that, hey, we can model things and we can use machine learning in order to sort through results of massively parallel modeling. And AWS means that we don't have to stand up your own cluster. As long as you have money in your account, you can pay Amazon for scaling your computation as much as you want. So for 20 years, there was a almost exponential growth of the computational capabilities. And by now, the vast majority of the screening workflows is essentially a funnel. We start with some form of search space, and then we go through the set of progressively more precise filters until we come up with the several candidate materials. And then these are passed on to the experimentalist, and the message is that, okay, now it's time to validate the theoretical prediction. That's a great step, but it's also not enough because ultimately we also need to learn from the experiment. And for the time being, this part is considerably less common. And it's understandable. We are not going to change the DFT based on the results of the single experiment. So in the experimental world, the inflection point was about year 2000. So before then, if you want to run the automated experiment, you need to build your own lab, like people like Lee Cronin or Benji Maruyama or Tonio Bonassisi has done. After that, it became possible to essentially buy a tool, install it in your lab, and you run your own experimental optimization. So the state of the art here is the myopic workflow, for example, based on Bayesian optimization. So we start with some parameter space, we perform measurement in this parameter space. Then based on this measurement results, we try to figure out what is that we want to optimize. We create the surrogate model of this process. Then we define how much we want to balance exploration exploitation, and then we choose our next experiment. So once I joined the University of Tennessee about almost 2 years ago, it actually had a pretty good history of the automated experimentation. So some of my colleagues worked on the combinatorial libraries and combinatorial laser processing for more than 15 years. So there was a good history of doing that experimentally. So Professor Amadi started the automated synthesis program in 2019. So she started with the single OpenTron robot. Now she has multiple robots, including those for thin film synthesis and characterization. So after I joined UT, my priority was to work on the automated experimentation in scanning probe and electron microscopy. So let me see how it goes. So Jay has mentioned an example of the using electron beam to create the letter ORNL. So this is another example of using electron beam to do the essentially 3D printing on atomic level to make a crystalline letter T. So my group worked on automatic SPM. So I think we are now the only academic location in US that build the direct connection between the SPM and supercomputers. So my colleagues build the same type of connection for the electron microscope. And the most recent addition to the group is the automated nano indentation that was we brainstormed and was built by our colleagues in the mechanical engineering department. So you can see how the computer vision algorithm identifies interesting features in the optical image, and then the nano indentation is done only in those locations that we care about. But then we realized that ultimately, if we have automated synthesis, automated filmmaking, and multiple characterization methods, we somehow need to make it work all together. It's not a single optimization loop. It's something much more complicated. And just borrowing the example of the workflows from Amadi Lab, so they work on the hybrid perovskites. So you start with some reagents, you can use them to make the combinatorial library through the robotics, measure optical properties, and analyze time, stability, what's not. You can make thin films, you can grow crystals. If you make films, you can study them by techniques like CL, TOF, SIMS, XPS, and so on. You can make devices. I mean, all of us who are familiar with how the labs work are familiar with this type of processes. Notice that nowhere here you are going to see a single optimization loop. The decisions that we make in the real world labs are much more complicated. For example, we can use microcrystal library to select the thin film, which thin film to make. This takes an hour. This takes 400. This takes several hours for one. So this is something that can be done using the standard Gaussian process or multi-fidelity versions. But very often we have to make much more complex decisions. For example, we need to analyze cathodoluminescence data, and based on that, we need to change the manufacturing or the annealing process for the film. Or we need to take the XPS data and based on that, change our systems. And when we make these decisions, we always make them based on the perceived gains, and we take into account latencies and cost, right? Some instruments are available in the lab. Some of them require going to the facility like Oak Ridge CNMS. Some of them require going to the synchrotron. So it's a very complex planning process. And the interesting thing here is that the latencies and costs are very well known. I can tell you how much each tool in the UT user facility costs. Latencies we usually have a very good idea about. The part which is curious is a perceived gain. How much XPS measurement is going to help me make the films better? That's the part where things actually are complicated. And in fact, if we look at how the real world works, we can sort of draw a picture like this. So if we start on the left, this is the material optimization in a single lab. So that's essentially a fundamental research. We use this knowledge in order to prototype devices. Then we get it into the production. So the important thing is that the economic value is created only on the production stage. And this economic value somehow propagates towards the materials discovery and towards theory. The fundamental knowledge is created usually on the basic discovery labs, and we use this fundamental knowledge in order to prototype devices and build products. The important thing on moving from left to the right on this diagram is that here things are usually happening fast and have a fairly shallow physics model. Things on this type are happening very, very slowly, and the physics models are usually not very well defined. Optimization steps spaces are usually very high dimensional, and so on and so forth. So we are not going to use Bayesian optimization to improve batteries in the gigafactories simply because it takes several months to test a battery, and nobody will let us play with the gigafactory for tens of years to do the naive optimization. So the real world operates through the network of the connected cycles, and these cycles are connected through the very high dimensional data sets, and the value of these data sets can be understood only down the line. When we generate them, this value is only probabilistic. So the question becomes, can machine learning help us work with this type of problems? And here I would make a very loud claim that machine learning and physics may be not enough. So let me illustrate. Imagine that you have this triangle where one corner is the data-driven methods, such as deep learning, whatever. The other corner is physics and computational methods. We have obviously techniques that span this spectrum. For example, pins, neural operators, structured Gaussian processes, they all leverage both physics and data-based methods. So is it enough? And I argue that it's not, because ultimately we also need the third corner, which is the reward. What is that we want to accomplish? Obviously, the long-term rewards are global warming minimization, better energy storage, and so on. These are very complex notions. So, however, if we look at what are the rewards in the ML and physics, how do we know that the ML algorithm is correct or the physics is done right? They're much more primitive. So typical reward idea in machine learning is the loss function. When we train the neural network, we want to minimize the loss. When we do physics, it's obviously more complicated, but in physics, criteria of the right theory is usually things like predictive power, parsimony, whatever. So obviously, most of the real-world applications are somewhere in between, right? So the manufacturing is complicated, material prediction is relatively simpler. So here we know whether we predicted right or not, relatively easier. So device optimization somewhere in between. Now the question is is it something that abstract, or do the machine learning people think so as well? And as the example of very strong confirmational bias, which I found in the book by Peter Norvig, who of course knows quite a lot about machine learning, is the introduction, where Peter says that somewhat remarkably, all AI research until very recently has assumed that performance measures can be exactly and correctly specified in the form of the utility and the reward functions. So machine learning works if and only if you know what you want to accomplish. My point is that in the real world, we typically don't know what we want to accomplish. And some of the concerns of scientists like Hinton about the negative effect of AI are related exactly to this point. So now let's assume that we want to make a next step in AI, not through the development of beta algorithms or through incorporating beta physics in the algorithm, but through the definition of the reward functions. And the point is that if the reward function is known, then all problems are optimization problems. And actually, we know how to solve optimization problems remarkably well. So let me illustrate how it works. So obviously, when someone tells you that, okay, I have this great new theory about how to make world a better place, there are two questions you can ask. So question number one, can the previous examples of the work done be illustrated in terms of this, interpreted in terms of this theory? The point number two, can this theory allow you to do something new? And let me illustrate that both in fact are true, and both work for microscopy. So for me personally, microscopy was the playground where I started to work on the incorporation of machine learning with my colleagues. So as Jay pointed, we started to think about it. In fact, we started to think about it before 2010. It's just we developed the nerve to publish about it by the year 2010. And we've done a lot of work by using the neural networks for image analysis and spectrum analysis and scanning probe microscopy. So that was 2009, taking the theoretical model, training it on the neural network on theory, and then applying it to experiment. And for the last maybe 5 years, we've been working on the automated experimentation. So can machine learning make microscopes better, right? So let's take microscope as a very special, almost toy model for the general material discovery. So how do people try to improve microscopy? So depending on what field you're in, you either try to minimize the probe damage or minimize beam damage. You try to improve spatial resolution. You try to improve stability. So these are microscope-specific requirements. They are very common across both electron and scanning probe microscopy community. When the manufacturers build the microscopes, these are the parameters they care about. When people give talks at the microscopy conferences, these are the things they try to improve. But for vast majority of the domain scientists, resolution is not the goal in itself, right? So we use microscopy to solve real-world problem, either better materials for nuclear reactor, or batteries, or direct air capture, what's not. So the question becomes, what are the rewards and what are the objectives? So imagine that you want to make a better material for the reducing global warming. Obviously, you cannot do it running a microscope experiment. So you start with the fact that, okay, this is our global objective, but in order to accomplish it, we probably want to create the cheap materials for grid storage. And in order to make these cheap materials, we need to understand how materials degrade. So ultimately, you can define an experiment when you run the electrochemical reaction in situ stem, and finally, you have an idea about what is that you want to accomplish on the specific day you're at the microscope. So the problem here is that each scientist plans the experiment based on combination of objective and being informed by prior knowledge, prior experience, and intuition. So how does it work? Imagine that you're in the lab and you're running the microscope. So the set of operations that you run is very simple, or this type of operations you run is simple. Essentially, it's taking images, zooming in, zooming out, taking spectra, then analyzing data. The number of possible operations that you can perform on the microscope is very limited. It's essentially tuning, scan initiation, probe positioning, taking spectrum. The number of operations a human operator does in a single day can be very significant. It can be hundreds and thousands. And the key thing is that it's not a random actions. These actions are informed by prior knowledge, and they are driven, so you try to get towards some reward and objective functions. And my point is that without understanding what these reward functions are, we cannot have the machine learning driven experiment because our agent doesn't know what to do. However, once we have this dichotomy, it becomes relatively easy to classify what are the levels of the machine learning in microscopy or any other physical characterization experiment. So the lowest level is so we start with planning experiment, making sample. This is our day on the microscope. This is the data analysis. So the earliest stage of the machine learning is the post-acquisition analysis. In this case, no matter what we do, we cannot go back to the experiment. We can only plan a new experiment. So in some sense, this is the part where the added value of the machine learning is an understanding, but it doesn't affect our experiment planning. The second level is the real-time analytics. When we have the microscope, we stream the data, and then the data can be either a lot of it or it can be very high dimensional. So the role of machine learning is to convert it to the representations that are convenient for human, but the decisions are still made and orchestrated by human. ML just helps us present the data. And then the third level, where we talk about the autonomy, or at least limited autonomy, is when the machine learning agent makes decisions and uses this decision to run the microscope. That's when we start to have the autonomous tool. Now, there are fourth and fifth levels. So these are how does microscopy connect to other fields? For example, what is our downstream use of microscopy, or whether the microscope can inform the device that makes samples. So currently, my lab builds a prototype robot when the microscope tells the simple syringe-based pump system what material to make. So with this being said, if we consider only a third level of the ML in microscopy, meaning the active learning, our process becomes a workflow. So we essentially represent the operation of the microscope as steps like select image, taking spectrum, and so on. And then in order to implement the machine learning workflows, we need to do two things. We either need to define policies, meaning provide some set of kind of operation table. This is what you see on the screen. This is what you should do. Or we should provide the rewards. So providing rewards means that the microscope should actually learn the policy that's required to accomplish or maximize this reward. So the reward can be available on each step of the process. This is the myopic or Bayesian optimization workflows. The reward can be sparse, meaning that it is available in the end of the experiment. That's kind of more complicated. But if we don't have rewards or policies, if we only have objective, machine learning just doesn't apply. We need to have the rewards or policies defined, and then we can build machine learning with workflows. So what can be reward functions in imaging? So let me show you a few examples when we kind of look in the past. So the obvious reward is the physics learning, right? So we have some physical process. We want to understand what's the physics behind it. So simple example here is the ferroelectric domain switching. So we have the tip, we apply bias, it creates the ferroelectric domain. We have some hypotheses here. So this is how it works in real time. And kind of our colleagues in the machine learning community always talk about the autonomous AI scientists as something in the future. Maybe it is not that, maybe it's not in the future, because strictly speaking, what we have here is the fully autonomous system where we provide a list of hypotheses and it runs the experiment to figure out which of these hypotheses is correct. So it plans the experiment and it runs the experiment. Obviously, it's a fairly modest implementation, but it doesn't change the fact that it does exactly what is advertised. And this is the example of the data analysis in this experiment, where we figure out which of the hypotheses ends up being the correct hypothesis overall. So you see that we have 4 hypotheses, and here it's clear that after 40 stages of the process, model number 3 ends up being the one that is the correct one. So once I moved to University of Tennessee, we decided that it's time for us to build obviously purpose to build the autonomous machines for the materials discovery. So we integrated the Asylum Jupyter SPM with the ISACs, the UT supercomputer. So Oak Ridge, it took us 4 years. Now things are becoming easier, so it was just half a year. And now we can run much more complex workflows for exploring the combinatorial libraries. So combinatorial library is essentially a sample where on the one end you have one material composition, on the other end you have another composition. So it's basically a cross-section of the phase diagram. And what you see here is the video of how the microscope works. So in this case, it actually does much more than one operation. So we had not only to move the sample, but we also had to figure out whether we do measurements on the right region. We had to develop the workflows that allow us to tune the cantilever and spectroscopy. So it took quite a while there was a lot of false starts. So many things worked maybe 8 months ago, but then it turns out that you always need to add something else. And what you see here is actually the discovery in this combinatorial library. It looks like it's a simple Gaussian process, and in this case it is, but each point here is not coming from acquiring a theoretical model or pre-recorded data set. So each point here is an actual measurement when the Gaussian process actually tells the microscope where to take the measurement. And in the end, you can see that we found a region where there is a increase of the properties. That's exactly the reason of this morphotropic phase boundaries. And now we are playing with extending this approach for structured Gaussian process kind of different ways of how you can take the noise into account between measured, heteroscedastic, and so on. And there's a few more examples of the automated microscopy running. So this is mapping of structure property relationship through the DKL. This is a very cool example of the optimization of the instrument. That's important because there are about 100,000 AFM in the world, and multiple hours a day are spent by human operator to actually optimize it. And this is the example of the simple video where we run an experiment with the fixed policies, where we basically tell the microscope to take the measurements only on the domain wall. So you see that we have a region of material with very complex microstructure, and our microscope goes through location one by one and takes the measurements at the same locations. So obviously we can do the same type of things at the electron microscopy. So this is work that we've done in collaboration with the Thermo Fisher. So first through the Gatan interface, and then through the Thermo Fisher interface. And in this case, the experiment is that, okay, let's take the nanoparticles, let's segment them using the SAM model in real time. And now we can basically tell the microscope that we want you to measure yields, EDX, and diffraction at centers of each nanoparticle. So rather than doing measurement on the grid everywhere and waste a lot of time and effort, we basically examine one nanoparticle at a time. So if your goal is to characterize the chemical and physical variability of this nanoparticle system, your acceleration rate compared to the grid measurements of human operator is something about 100. So we want to be modest about it, because one has to be very, very careful with the concept of the benchmark in the active learning, because if one thing stops being a bottleneck, then something else starts to be a bottleneck. But again, in this case, we benchmark with respect to human, and the acceleration rate is significant. So then the question becomes, how can we use the reward-based models here? So, okay, we know how to segment images. So we learned how to do it on the static data, pre-acquired data long time ago. We learned how to do it on the real-time data in 2021. And of course, by now, it probably makes sense to fine-tune the SAM or SAM2 rather than write your own model. So the problem is with the deep DCNNs that they're supervised, they're black box, and then they're not robust. And then we decided to do the following thing, like, okay, there was a world before deep learning, right? Even though sometimes it's difficult to remember this world. So how did we find atoms before deep learning? The answer is we used the simple functions like Laplacian of Gaussian, very simple operation. Why did we stop using them? Because they require manual training. And the imaging conditions change a little bit. These workflows are not very robust. We need to manually retune them. And then we asked ourselves a question. What if rather than using the supervised DCNNs, we use the optimized simple tools? Can we do that? Does the reward function concept allow us to go back to use simple tools? So how do we do that? We need to introduce rewards. So the rewards and analysis of the atomically resolved images are fairly simple. It's the number of atoms in the field of view, and we know that reasonably well. We can introduce rewards that atoms cannot be close to each other. And then it turns out that the problem of finding atoms becomes a problem of the optimizing of log in the four-dimensional parameter space, given the two reward functions. So we get the Pareto frontier that balances them. And then it turns out that it actually works remarkably well. In fact, we benchmarked against the CNN, and it actually less sensitive to the noise than the CNNs. Obviously, again, I don't trust the benchmarking done within one group when we provide both versions of codes and the benchmarks, but at least it works. It definitely is not worse. And it's also very easy to implement in real time. So this is the example of the spectra, and then we have this reward building based workflow running in real time. And the great thing is that it's explainable, and it's fairly robust, and it's reasonably light in terms of computation. That being said, the question is, can we do something new, right? So, okay, now we show that reward-based workflows can solve the same problems as DCNNs, at least for atomically resolved images. Can we do something new with them? And the typical problem that we have with the image analysis is to find what is that inside the image. So this is, for example, the electron microscopy image of the yttrium copper superconductor. There is some radiation damage here. So if you look very carefully, you see that this part of the image are a little bit more diffuse than this one, basically at the limit of the human perception, even for the qualified operator. Can we use the reward-driven workflows in order to identify this region? So supervised learning is not going to help us because we simply don't have training examples, and even human perception is not good enough to provide the data set. How do we analyze this type of images in the unsupervised manner? Very simple. We start with the image, we create descriptors. So a typical way we do it is we find atoms and then we take image patch centered on the atom. Then we do some form of transform, either nothing or radon or Fourier. Then we do the dimensionality reduction. Then we get a map that shows the weights of these transforms. The problem with these workflows is that they are fairly complex and they're also non-myopic. And in fact, if you kind of 15 years ago when we started, the problem was how do you analyze if you have a lot of data? The problem now is that what is the right analysis method to pick up? And the workflows can be very complicated. There is a tremendous number of ways how we can create the key points, tremendous number of ways how we can create the descriptors, a whole bunch of ways to do transforms, clusterings, dimensionality reduction. So how can we do it systematically? And then we propose that, you know what we need to do? We need to define a reward. If we know what our reward is, so how we conclude that analysis is successful, which conveys the human perception and a kind of combination of human heuristic and knowledge of physics, then all our problems becomes an optimization problem. All we have to do is we have a combinatorial problem of the definition of the workflow and then the optimization in this joint parameter space of all these operations. And if we do that, then instead of the process that is non-myopic, so operation here affects the results here, and sensitive to distribution shifts and essentially black box, we have a workflow which is unsupervised, robust, and explainable. An interesting thing that it works. So these are just few examples of very few cases where we have a ground truth. So depending if we do the analysis right, we get something like this. If we do the analysis wrong, we get something like this. The important thing is that this is a fully automated process. There is no human involvement beyond the reward function. And it works for more complex problems like finding ferroelectric domains. So for example, if I want to find the ferroelectric domains, what are my reward functions? From the physics considerations, I can say that I kind of want the domain walls to be relatively short because they come with the free energy. And I want them to be relatively flat because all the bands are associated with the depolarization energy. So I can take the image, I can make this as a reward functions, I get the Pareto frontier, and then I can look how my segmentation results look on the left and right of the Pareto frontier. So it's kind of looks like the optimum is somewhere here. Now, what's great about the reward-based approaches? The great thing about it is that it immediately allows us to build the human-in-the-loop methods. So let me illustrate how we can think about it. So these are the example of the automated experiments from the Oak Ridge time when we have the exploration of the nonlinearity. So this one looks like a plausible result. This looks like our algorithm clearly gets stuck into locations. So what's going on? The problem is that we define the things like balance between exploration and exploitation and reward functions before the experiment. So it turns out that for the myopic workflows, we naturally have ways to inject human in the loop. So the simplest way to do it is through the reward function. We can run the automated experiment having the idea of what is success. But during the experiment, we can tune this definition and see how the experiment progresses. We can also balance the exploration and exploitation. So in the beginning of the experiment, we can say, hey, I'm just going to explore things. When my time runs out and I just have half an hour to get good results, I say, hey, let's go greedy and make our algorithm as greedy as possible. We want to just get results. Standard problem in AI is that it's not explainable. Is it a problem for experimental sciences? Well, yes and no, but keep in mind that the all human build equipment for the time being is designed for the human operator, which means that it's kind of oversimplifying, but in some sense, we don't have explainability in the automated experimentation problem in the automated experimentation because we are used for human doing everything. We just want to make a step beyond human. And we can observe things like real world trajectory, feature spaces. We can see how fast our model learns. And that basically allows us to build the human in loop experimentation. So this is the human in the loop experiment when our ML agent controls the microscope. So this is not a simulation, it's a video of the real human operator telling machine learning agent what to do, and then machine learning agent tells the microscope what to do, and the human operator basically change the policies of the machine learning agent. So it works. And that becomes kind of interesting because the current generation of tools and all the tools developed before now were based on the human telling, orchestrating, and planning the experiment through the basic commands, and the human having kind of seeing what happens on the instrument screen. So what you saw just now is the illustration of the machine learning agent that issued the primitive command to the microscope, and the machine learning agent analyzed the data. The value proposition here is that the electron microscope can generate data about 1,000 times faster than human can make decisions. So this inner loop gives significant acceleration compared to human operator. The human in this case basically changes the behavior of ML agent, and I've just shown you how it works. So what would be the next step? And the part which is very, very interesting for me is once we kind of connect to the folks working on the LLM type of approaches, where we basically use LLM to plan what the reward functions can be. So for the time being, all reward functions were either simple or physics-based. I'm pretty sure that we can do better. So what are other opportunities or challenges? Now imagine that you have two tools. So you have a combinatorial library. You can study it using scanning probe microscope. You can study it using Raman. So the question is, do we want to do it sequentially, or can we derive value from running the SPM and Raman at the same time? Notice that it doesn't have to be the combinatorial library. For example, this can be the automated synthesis robot, which can allow us to explore very high dimensional spaces, not like 3 or 4 dimensions like combi libraries. So if my point is that if we want to run multiple tools at the same time, we need to identify common rewards. If we don't know how to compare apples and oranges, we cannot quantify the extra learning extra benefit from running things simultaneously. So if we have the automated labs, when we have multiple synthesis robots and multiple characterization tools, we will not be able to coordinate them until we understand the gain of value. Same thing applies for theory. So we always talk about combining theory and experiment and theory on the fly. It is super difficult because we need to compare apples to apples. So they have to operate over the same object space and make comparable predictions. But we also need to figure out what are we going to do? How are we going to adjust the theory given the experiment? Otherwise, it's incomplete. So reward functions here, and in this case, we also talk not only about rewards, but balance of beliefs, but it's still a big part of it. Now, just to give some broad perspective. So there is no doubt that big data and associated infrastructure and foundational models are absolutely key, especially in the fields which are well established and mature. If doing science means going to where no one has gone before, we are not going to have any big data there because it's simply a new thing. What we think will make a difference is the reward functions that define how we run our experiments. So we don't know what the results are, we don't have data, but at least we can distill the best practices of how to make our instruments work to get this data. So that would be a big part of it. And as I mentioned, the value proposition here is simply that many tools can work much faster than humans can. And at least for the time being, all the AI models demonstrated the saturation at the level slightly above the average human. And obviously, as the domain experts, we expect that we operate on the level well above average human, because otherwise, why are we doing it? So in this case, the reward function approaches is probably something that will allow us to move in somewhat orthogonal direction. And just to finish it, how would the labs of the future look like? So let's say in 10 years by now. So once you start to think about the fact that if we have multiple integrated tools, they have to be collaborative between the human and AI. It's co-scientists. They have already been demonstrated in multiple fields. Obviously the paper by Gabe Gomez got a lot of visibility, but practically co-scientist tools are in some form built by many groups. And in some sense, ChatGPT is a co-scientist. We have some objective that we want to accomplish, which are probabilistic. So if you combine all these elements together, it hopefully looks like that the interface for the lab of the future would be like a giant role-playing game, because the type of challenges we have are exactly the same. And that can be a kind of super interesting time to be at. So thank you for your attention, and I will be happy to take questions.
That's fantastic. Thank you so much, Sergey. It's a great talk. So I think for the purpose of questions, just because there are quite a number of people on the line, maybe we could have people raise their hands in the Zoom chat, and then we'll operate through that mechanism. So any questions from the audience, feel free to raise your hands. All right, Raphael, please unmute and go right ahead.
Thank you so much for the talk, Professor. Could you explain a little bit more about how you could make a reward to make the path to choose different models to obtain the results? How does that work? Could you talk about that a little bit more?
Yep. So defining reward functions, as you can imagine, is super difficult, because we were lucky to start from the atomically resolved images. In fact, historically, my background is scanning probe microscopy. Most of the work that I've done with machine learning always started from electron microscopy, despite the fact that it is much more expensive in terms of tools and so on and so forth, simply because the physical meaning is much more shallow when you work on the atomically resolved images than with the mesoscale images. So it's just simpler. So the reward functions on the atomic level very often are physics-based. And interestingly, many of them, if you kind of think a little bit about it, many of them are the same criteria as the human scientists will use to ascertain whether the result of the experiment makes sense or not make sense. So it's not purely, some of it is physics, some of it is the human heuristics, but it's a human heuristic that has been informed by physics. And that's the reason why we were able to actually make it work in this first place. So once we go to the more complex systems, the heuristics becomes more complex, and at some point, obviously, we will not be able to create the reward functions. For example, I don't think that we can create a reward function that identifies cats on the internet, even though the AlexNet does it remarkably well. But for all the cases that we dealt with, the reward functions were able to create if you spend enough time with the domain expert. Like if we work on the synthesis of the hybrid perovskite, the easy reward function, that solution should not become yellow, because that means that lead iodide form. If you run an AFM, you really don't want to see the certain type of the noise patterns in the image, because that tells you that your mechanism is kind of not super good. We also know that there are reward functions which are something that we haven't put our finger on yet, but we know that are out there, because depending on the certain imaging conditions, our probe can fall apart very rapidly, or it can work for a long, long time. And we suspect that in this case, the reward function need to be extracted from the observation of the cantilever oscillations rather than the images. So it's not a universal process. it's heavily domain dependent. But the thing that makes us optimistic is that we know that if we know that we cannot use supervised machine learning to make AFM imaging better, simply because everybody look at different samples, so supervised learning just doesn't apply. We also know that human operator can be trained to be a pretty decent microscopist within half a year, and the human expertise is transferable. So there is something about how we do experiment that is transferable from human to human. The reward function concept in this case is basically trying to distill the way human identify the quality of data from the data itself by code, as opposed to kind of gut feeling of the human operator. And for the time being, it seems to be working. We don't know where it will stop. So obviously, there is no magic. There is no silver bullet solution. Maybe some rewards are clearly probabilistic, but the important thing is that we simply have not explored this aspect systematically. So that's a very interesting direction to move into.
Wonderful. We have time for maybe one more question. Is there anyone else who would like to ask? If not, I'm going to take my liberty. I was thinking about your, let's call it reinforcement learning based optimization of the modeling architecture. Right, you've basically got a modeling workflow, and now you are attempting to optimize this. And this is something we talk about in class often, that there's no optimal number of K for clusters, or at least using things like elbow method don't work. I'm wondering why this works better in a reinforcement learning context than it would in a more standard Bayesian optimization, whereby you're now exploring model space.
So notice that for both reinforcement learning and Bayesian optimization, we need to define the reward functions, right?
Yep.
So I had an interesting collaboration with the folks in the Google Brain for 2 years, and kind of the group of the, by the way, with the that was closely connected to Aaron Curville, and kind of after a while, I started to realize that, I mean, obviously, when you hear about reinforcement learning, there are a lot of moving elements that you need to learn and understand on somewhat intuitive level before you can even use it. But then I realized that my problem with the once I actually learned how to use it for simple things, I realized that I don't understand where the rewards come from. Then I talked to the Google people and I asked a question like, look, I kind of finally figure out how to make things work. Where do the rewards come from? Like, am I stupid or not? And then said, no, you're not stupid. That's actually the most difficult problem here. The point is that in most real world situations, we don't have reward functions. So our colleagues in the IT world understand it. That's why they're concerned about alignment problems and kind of AI rising and killing all of us. It's a legitimate concern. That being said, we are experimentalists. We are coming from the totally different end of the spectrum. Our problem is not that we don't know reward functions, because we have been doing science as a community for 200 years. Our problem is that we don't know how to formulate them in the form that machine learning algorithm can also do that. That's the challenge. To go back to your original question, I speculate that RL-based scheme are somewhat self-correcting. So you have a spectrum of action and states, you have a spectrum of the reward functions. In the end, they may have a higher potential for self-correction. Once you deal with the Bayesian optimization, you are kind of stuck with what you have. So if you didn't choose your reward function correctly, then you will just accelerate. It's like the difference that if you walk or you drive a car, imagine that you drive a car on the road and you cannot turn your wheel. So in this case, you can get fairly far if you choose the direction correctly and the road is straight. But if the direction is chosen wrong or the road is bending, then it ain't gonna work. So with the reinforcement learning, you have a little bit of the feedback from the environment. If the feedback mechanism is correct, you will learn. So you learn the right policies. If your feedback is incorrect, of course, things will kind of crash and burn. But that being said, I think that we have kind of three big problems, right? So the problem number one is the problem of descriptors. So our colleagues in chemistry, chemistry generally have a much kind of longer history of successful use of machine learning because the descriptors are well defined. You start with smiles or selfies, whatever. When you work with materials, the descriptors are not very well defined. And it's very difficult to build ML algorithms that operate with the diffuse descriptors. The second problem that we have is actually the problem of the reward functions because we can solve individual tasks without them, but not put tasks in the workflows. And unless we can build multiple interconnected workflows, we are not going to have a truly autonomous labs.
Fantastic. Okay, so we're 3 minutes over our time. Sergei, thank you again for the presentation. Thank you for agreeing to do this. And
My pleasure.
yes,
Thank you for the invitation.
awesome. Thank you.
Bye.
Bye.